Hello everyone, good morning. So in this talk I would like to tell you about quantum money and really why quantum money isn't really about money, it's about quantum cryptography. So let's just make sure that we remember yesterday. We are going to really use a set of minimal quantum gates, the bit flip and the Hadamard gate. So we remember that bit flip takes a classical state qubit and flips the bit, and the Hadamard gate just really gives us a basis change from the computational basis to the Hadamard basis. And two more things is that we remember that pure n-qubit quantum state are just really unit vectors in complex space of exponential dimension. And we are going to think a lot about mixed states, or you can also think about them as classical probability distributions over quantum states. Just for every quantum state, there is a classical probability to get this state from this distribution. Okay, so I would like to start with like the basis for all of this talk, which is the no-cloning theorem. So the no-cloning theorem, I think that Giulio talked about it a little bit in his talk, says that there is no one quantum operation that is going to be able to clone any input quantum state. And if we think about it from a perspective of complexity, this is really a worst-case statement, right? It says that for every algorithm that tries to clone the input quantum state, there is going to be an input that is a quantum state, an n-qubit quantum state, such that the cloning algorithm is going to fail on it. But we want to talk about cryptography, so the connection to cryptography and the no-cloning theorem, I'm going to do two relaxations to the previous statement. So the first one, I'm going to ask that this is not going to be any possible input to the cloning adversary. It's going to be an efficiently sampleable distribution over quantum states. And the second relaxation that I'm going to do is I'm not going to ask that A is going to be able to clone with probability 1. It's going to be able to clone only with non-negligible probability. And it turns out that this is actually also easy to prove, also impossible. So this is a basic example of how easy is it to get average case hardness from quantum information. Let's see a formal statement. So there is a quantum polynomial time algorithm Q, which we are going to think about as the sampler of this distribution over unclonable quantum states. And for an input security parameter n, it's going to sample an n-qubit state psi. And it's going to be for any possibly unbounded quantum algorithm, it's going to be impossible to take one copy of psi and output two copies. It's going to happen only with exponentially small probability in the security parameter. And actually this sounds a bit mysterious. There is an algorithm, there are many algorithms for Q, and it is relatively easy to construct them. Okay, so how does this statement in quantum information theory goes back to reality in cryptography, and the vision of quantum money, which I forgot to write here, was by Stephen Wisner in 1969, was that let's think about it. What's the implication for a quantum system? So let's say that I just sampled an n-qubit unclonable quantum state and I put it in this register. And this quantum register, this quantum system is going to be a rare physical object because this is unclonable. Once it's destroyed, I cannot just miraculously produce a new one. Also states, quantum states generally, we can think about them as if they take very small physical space, and also they can be transferred through communication channels. Let's assume quantum communication channels. So they are very small, take almost no space, very easy to transfer, and that really gave rise to this vision by Stephen Wisner, which was only the first killer app, I think, of quantum cryptography, or one of the first killer apps, is that we can think about these quantum states as idealized digital cache. So what we're going to see in this talk, we are going to see a definition, we are going to see that, as I promised, quantum money is really about quantum cryptography. That And then we're going to construct the easier part, which is private key quantum money. We're going to see how to sample unclonable and verifiable quantum states. Then we're going to move to public key quantum money. We're going to see two techniques, which we are going to talk about later. And at the end, we are going to see how to construct public key quantum money in the standard model using computational assumptions. And that is going to involve looking on some key and basic techniques in this field. Okay, so what is a quantum money scheme? This is only two algorithms, two efficient quantum polynomial time algorithms, a generator and a verifier. And the generator is going to take in a security parameter, this n. It's going to output secret classical key and a quantum state. And the verifier is going to take inside the secret classical key and a state, a presumably legit state, which the verifier is going to attempt to verify, and the verifier is going to output a verification or acceptance bit, B, and it's going to output a quantum state. Maybe it's going to preserve the state, maybe not. Let's see under what conditions. Yeah, I didn't say this, but please ask questions if anything is not completely clear. Okay, so what do we expect from correctness? This is just a sanity check. If we sample the state correctly with accordance to the generation algorithm, what do we expect the correctness to the outcome of the verification? We are going to expect the verifier to output 1, and the state to be preserved. This is just, and this should always happen. Okay, what about security? So this is where the no cloning theorem comes into our favor. So we are going to ask that for when the generator samples the secret classical key and the state, it's going to give one copy to any quantum polynomial time algorithm A. And this algorithm tries to output two quantum states. It does not necessarily try to clone. Only with a negligible probability, both states are going to be verified by the verification. So just make sure that you understand that this is a bit easier possibly to do than to clone. You might not be able to clone, but you still might be able to trick the verification. And this is just the correctness and security definitions of quantum money. So why did I say that quantum money is really something more general than that? What is this definition tells us? This is just an efficiently sampleable distribution over quantum states, which has two properties. It is verifiable given the secret key, the secret classical key SK, and it is also unclonable. And given this general and simplistic description of quantum money, you can actually prove that a lot of, or even all of the primitives that I can think about in quantum cryptography, they imply this private key quantum money. And just like, for example, just like we think about classical one-way functions as a precondition to classical cryptography, we can think of private key quantum money as a precondition to a lot of quantum cryptography. And the upside of this, another upside, is that a lot of the time when we actually make a technological breakthrough for quantum money, we get these breakthroughs for many of the primitives in quantum cryptography. So if we care about quantum cryptography, we should care about quantum money. This is my claim here. Okay, so let's construct private key quantum money. Okay, so what we want to do is to, as said, efficiently sample a quantum state that's verifiable and unclonable. Okay, so let's see a proof for a simple case of the no cloning theorem. I think that Giulio showed the exact same claim yesterday, so we're going to go over it quickly. Look at this set. We are going to have the two classical states and the two Hadamard states. What I'm claiming is that there is any unitary on 2 qubits, U, that's going to take an auxiliary qubit 0 with all of the states in S and always manage to clone. right? This is what we're seeing. Just a cloning unitary on n qubits, on 2 qubits. Let's go over the proof quickly, because we saw it yesterday. Okay. So if we have such unitary U, we know that U in particular clones the plus state. It's going to take as input plus and 0. It's going to output 2 pluses, which when we think about the vector is this vector. Another thing that we know about the plus state is that it's in the span of 0 and 1. That's one thing that we can say. And another thing that we can say is that U successfully cloned both of them. So we're going to use the fact that U is a linear transformation, and U clones plus, and we can think about plus as this linear combination, and then apply U, the linearity of U. Make sure that this compiles. Right? This is the equality where I use the linearity of U, not even the fact that U is a unitary matrix. And I can say that U successfully clones 0 and 1, and this is why these two turns into just a cloning of 0 and a cloning of Y. And if I just think about the vector, these are not the same vectors, but these are the same, presumably supposed to be the same vectors. Okay. Okay, and another thing that we are not going to prove, which is a bit just a messier proof, but sort of the same ideas, is that we can have a cryptographic version of this 2 qubit unitary statement from before. So if I'm now looking at S, and I'm looking on a distribution, a uniform distribution over S, this is to have more of a cryptographic flavor. There is no algorithm, so there is a constant, such that for any quantum algorithm A, even if A runs in double exponential time, I don't care, A is going to take one sample from S, which is going to be a uniform sample out of these, and try to clone. This is going to be bounded with a probability about 1/2. Okay, so now I want you to help me to construct a private key quantum money scheme. I want to know how to sample an unclonable state and how to think about a verification key. Yes, Shweta?
Previous slide, please.
The previous statement.
Yeah. So in this set S, why should we have 0 and 1? Because we're picking uniformly, right? So with probability half, it will hit either 0 or 1. Mm-hmm. And these we can clone.
So what you're asking is, if I'm looking at a different set, different S, which is just a uniform distribution over plus and minus, is this unclonable or not?
Yeah.
Okay, so the answer to this is no, and the reason is this. If I know the basis in advance,
oh, I see.
Right? I know that the basis, I know it's either going to be plus or minus, and because it's either, okay, but this is a great question. So let's make sure that we understand why I'm actually, this is a crucial point, that I'm using two different bases, and what I'm really using is I'm sampling the base at random, whether I'm in the computational or Hadamard basis, and after I pick my basis at random, then I pick the element in the basis at random. And if I know that it's either plus or minus, or it's equivalent 0 or 1, let's say plus or minus, I can do a Hadamard gate, turns plus into 0 and minus into 1, and then I can just measure and know which one I'm. Make sense? Yes, Nico?
Can't you just say that if you know the basis in advance, it's just classical cloning?
That's, yeah, but yeah, that's reduces to classical cloning after you do the basis change. Yeah. Okay. So we need the fact that we're using at least two different bases. Okay. So how? Again, yes.
One more question. I assume that C is greater than 1 because otherwise the bound is trivial.
Right. So C is about 2. C is about 2. It's about the probability to do this is exponentially close to 1/2.
Okay, thanks.
Yeah, that's an incomplete statement. Yeah. C is about 2. Okay, so I know that if I'm sampling 1 qubit uniformly at random from S, I'm going to get an unclonable state. And another thing to hint about how to construct private key quantum money is that I can think about the choice, my choice, which is like 0, 1, plus or minus, as a classical description of the state. So how can I sample a private key quantum money state? And it needs to be n qubits. So if I have 1 qubit state, which is unclonable, if I'm going to sample n IID samples from this state, it should also be unclonable intuitively, right? And this is exactly what I'm going to do. So my secret key is going to be which states I sampled from S, which is just 2 classical bits of information, right? Which basis I chose and which element in the basis. And then I'm going to sample, and it's going to come down to this. Right? Make sure that this compiles for you. So the A are the choices for the basis element, and the B is the choice for the basis. So if B is 0, I'm going to do H to 0. Let's look on the first qubit. I'm going to do H0. So this is just going to be a classical bit, which is going to be determined by A1. And this is for all n qubits, which is just going to come down to this computation. Very simple. Like n parallel X gates with accordance to the bits, to the classical bits in N, in A, and then H parallel executions, n parallel executions of H with accordance to B. Okay. How do I verify? Okay, let's look at this equation. So I'm taking in order to create my state, I'm going to take a quantum state which is in the classical state, just n zeros, and I'm going to apply X gates and H gates. And we know that quantum computation is reversible. So what I can do, I can just reverse this computation, and not the slides, reverse the computation, and ask if I got 0. So let's make sure that if this thing is the actual quantum money state, so it's going to be this state, and if I take this and plug it in here, the H is going to cancel out with the first part of the circuit, and then the X is going to cancel out with this, and I'm just going to get 0. Okay. Okay, good. And just a security proof sketch. Let's go over it quickly. I don't think it's that interesting. You can look on it later if you care. The verification is projective, which means that this is a very nice property of this specific scheme, is that if I manage the verifier says yes, essentially this is the state. So outputting 2 quantum states that both of them pass verification means that I actually clone the state. Okay, so if I clone this n qubit IID samples from S, and this is an implication for this projectivity, this is the projective verifier. Okay, so I need to clone all n qubits. If I need to clone the n qubit state, we know that we remember the 1 qubit cryptographic no cloning, and it's going to tell us that for a C, for example, that equals 2, the maximal probability that you can clone this uniform sample from S is going to be about 1/2. And then because these are IID samples, this just scales exponentially. Okay, very simple, very clean, I think, up to this point. Okay. So let's ask a bit more from our scheme. Until now, this is not very functional, right? So if I have this, for example, the person on the right, Alice, has this valid quantum money state, and it sends it to the other side, Bob, Bob cannot really do anything with it. It cannot even verify. So private key quantum money is a nice starting exercise for something a bit more complex. And what we really know that how can we verify this unclonable quantum state, because we want not only a verifiable quantum state, we really want a publicly verifiable quantum state. Okay, so here is the first question. If I publicize the secret key, so remember our scheme, I'm going to sample random samples from S, and the secret key is going to be which one's which are the samples. These are only 2 bits of information. And I'm claiming that you cannot just let everyone know SK if you still want the state to be unclonable. So how can I clone? Let's say that I have SK, the secret key, which is going to tell me the basis and the elements in the basis. How can you clone? So I'm going to give you another hint. Think about the generator. So the generator really sampled the secret key first, and then it did what? Excellent, excellent. Okay. So what the generator really did is just generating at random first this classical key, and then as a function of the secret key, generated the quantum state. So really, when you have the secret key, you can generate an unlimited amount of quantum money states. So this is a bad idea, right? If you have the key, you can clone. So it's called a secret key for a reason. Okay, another idea. Maybe just we can verify without the secret key. Is it possible to verify the state without a secret key? And this is a bit more tricky, but you can actually prove that you cannot verify the state without a secret key. And the reason to this is that if you don't have the secret key, I can sample a different quantum state that is going to have 2 properties. It's going to be indistinguishable, perfectly indistinguishable from the quantum money state. And it's going to be this state. It might be a bit counterintuitive, but this is a very nice fact from quantum information theory, that if you sample a random n-bit classical string, this is going to be perfectly indistinguishable from a random quantum state, for example, in this basis. You can, we're not going to go over it, but you can prove that a single sample from S is perfectly indistinguishable from a classical bit, which really comes down to this. You look at this distribution, this is the uniform distribution over S, and uniform distribution over a classical bit, and they are the same. Which is weird, but yeah. Okay, so it seems that secret key quantum money is kind of trivial to construct, but it doesn't give us much. And this public verification problem, it was open since basically Wisner first thoughts about quantum money. And the first breakthrough was by Scott Aronson and Paul Cristiano. It was about 40 years later. We are going to see the solution with respect to an oracle, and then Mark Zandri came with the proof that you can actually take the construction of Aronson and Cristiano and use computational assumption to prove that this is secure in the standard model. Okay, so now we have a new goal. Now we have a new goal, and this goal is to sample, efficiently sample, a quantum state that's going to have public verifiability and unclonability. And again, a bit of motivation for public key quantum money. If we think about a lot of public key quantum cryptographic primitives, they also imply public key quantum money, and the same relation from before. This happens a lot, actually. Every time we have a breakthrough for public key quantum money, we almost always have a breakthrough for all of the other primitives in quantum cryptography, which are like public key quantum cryptography primitives. So this is the definition that we want to construct now. Just everything the same. The classical key from before is now public, which means that correctness essentially stays the same. Security, the only difference is now the adversary has also the public key. And it's going to be hard to output to states such that both of them pass verification. Yeah, so a bit of planning, what we're going to do. We're going to have a few steps to form some intuition and construct the public key quantum money scheme from Aronson and Cristiano. We're going to state security with respect to an oracle and then use Zandri's techniques to show that you can instantiate this in the standard model. Okay, new goal. Public key quantum money, we need to state what is the state, what is the classical public key, and what is the verification. Okay, so this is one tool that we are going to use in this talk, and in the next one, yes.
Question. Now, verification, do you still have to be able to say the same one you got when you verify it, or not?
Oh. Yes. So the question was if we're looking at the definition of public key quantum money and specifically on correctness, whether we are going to preserve the quantum state, and the answer is that we do. So if we sample the state honestly, the verifier is not going to harm the state. It's going to verify successfully and it's going to preserve the quantum state. Okay. So let's go back to indistinguishability obfuscation. This is an important tool for public key quantum cryptography in general. So this is an I/O for classical circuit that's secure against quantum adversary. What do I mean by that? A classical probabilistic polynomial time algorithm, when it gets a security parameter lambda and a classical circuit to obfuscate C, it's going to output another classical circuit, which is the obfuscation, let's call it O of C. And correctness states that functionality stays the same. So I took a circuit, I outputted the circuit, and these circuits have the exact same functionality. For every x, C of x equals O of O C of x. Security, if I have two circuits, and they are both bounded by some polynomial, and they have the same functionality, the obfuscation of C0 is going to be quantumly indistinguishable. Again, everything here is classical except this indistinguishability from obfuscations of C1. Okay, good. So some intuition about I/O. It doesn't hide really the function, but it hides how you do the computation, because two functionally equivalent circuits are going to be indistinguishable. In terms of instantiations, we know how to construct classically secure I/O. There are some candidates, partially by Nico and Giulio, how to do quantum secure I/O, which is the primitive that we're using. And for the next parts of the talk, until some point, we are going to assume ideal obfuscation. What do I mean by ideal obfuscation? It means that if I obfuscate the circuit, it's going to give you nothing more than oracle access to C. So you can think about it as really the best that you can do in terms of obfuscation. And sometimes, for some circuit, it really behaves like this. Okay, and one more, a bit of logistics before the technical parts. So, again, we talked about it yesterday. This is classical computation in quantum superposition. So if I have a classical function f from n to m bits, I have the unitary of f, which we denote by u of f, and it's going to take for any classical string of n bits. If I apply u to x and m zeros, it's going to move to x and f of x. Another thing is that if I'm going to say that I have quantum oracle access to f, I'm just saying that I have access to u of f. And as a fact important and simple fact to know that if I have a classical circuit for f, it is very easy to construct a quantum circuit, the classical description of the quantum circuit, U of f. in particular, if I have an obfuscation, which this is the important part, if I have an obfuscation of the classical function f, I can construct a quantum circuit that implements this u of f. And this is going to be our thinking from now on, how to construct public key quantum money. We're going to think of the public key as some ideal obfuscation for a classical function f, for n-to-n bits. And as I said, this ideal obfuscation that I'm momentarily assuming is going to give the adversary only quantum oracle access to f. This state, one thing that I'm asking, this state should be verifiable given the access u of f. And another thing is that this state should be also unclonable even given this oracle access to u of f. Again, this balance between keeping things unclonable but also now publicly verifiable. So this is how it's going to look. I'm going to have the generator output the public key, and the public key really just going to play the part as a quantum access to u of f, for f that we don't know yet. And it's going to be hard to clone like this, to forge. Okay, so let's try to have some intuition for what we're looking from this function f and from the state psi. So we want psi to be verifiable, we want it to be unclonable even given the function f, and we're looking really for f and psi. So let's say that if I took psi to be a classical state, that is clearly bad, right? Because I can easily clone classical states. If I'm taking the other extreme, which is going to be, for example, any uniform superposition, this is also in continuation to Shweta's question, this is also going to be bad because this is also easily clonable. But a nice observation is that if you take a set S, which is going to, you think about this S as the span of your superposition, and S is going to be random and not too big and not too small, this is going to generate a very good unclonable state. Let's be a bit more formal about it. If I'm taking a random subset, S, of let's say size 2 to the n over 2, and I'm outputting a uniform superposition over S, it is relatively easy to show that S is unclonable, given the random choice of S. But the good thing about this state is that S is going to stay, this cat S is going to stay unclonable even if I give you oracle access to membership check in S. Membership check in S, this is just a classical function that gets n bits of input and outputs 1 bit, whether the X is in S or not. And if I give you access to U sub S, this is still going to be hard to clone S. This is a claim without proof right now. Okay, so here is a suggestion for a public key quantum money scheme. And let's look on it, try to understand what's going on here. So I'm going to sample a S like this, a random subset of intermediate size, and I'm going to, the public key is going to be an ideal obfuscation of membership check in S. And now I want to verify. Can you suggest a verification for this state, this cat S? Now I'm the verifier. I'm getting some state cat phi. What I can do is to send it to the oracle U of S with the concatenated 0, and then in the right qubit, I'm going to have the answer in superposition over the x's, whether x is in S or not. That solves my problem, right? I can measure this qubit. We know from yesterday that if I measure this qubit, this one qubit here, this state is going to collapse to all of the x's that are inside S. And my verification is going to be If this qubit is 1, I'm going to verify, and if the qubit is 0, I'm going to reject. And this is great because if I get cat S, and I'm going to do this process, I'm going to send S and 0, and I'm going to get here just 1 because all of the vectors in the superposition are going to be inside S. So this is just a classical qubit here on the right. And then I'm going to measure it and see 1 and S. So I have correctness, essentially. Right? This is a proof for correctness. And I should also have security. Okay, so we have correctness. Let's just remember why we should have security. So I stated earlier that if I have this random choice over S, and I'm going to give it to any even computationally unbounded quantum algorithm A star, it's going to be information theoretically impossible to clone S. Impossible. Okay. So, yes.
Just a very short question on the previous slide. So you also have to output the quantum state S again, right?
I also, if correctness states that if I get the correct state, I should output the same state.
Yeah.
Let's make sure that it compiles. So if I have S, this is the legit money state. All I'm going to do, all the verifier is going to do, it's going to concatenate a 0, and then it's going to take this S and 0, input it into this US. We know that US just computes in quantum superposition the classical membership check. So we know that for all elements here, this is going to be 1. So this state is undisturbed. Does it answer the question, or?
I guess I'm not 100% sure like how we get the cat S out of that, or if it's already the left-hand side of this expression you have there. So it's
what you're not sure about?
So the input is this cat S, and the output should be something like 1 and cat S. And I'm not 100% sure where you get the cat S back.
Okay, I get it here. Let's recall what this oracle US is doing. All that it's doing is when I send any superposition and 0, I'm changing this qubit. For every X in the original superposition, I'm going to have the bit here in this cat, the classical bit, indicating whether X is or isn't inside S. So when, going back to correctness, when I'm inputting this state, cat S, which is just a uniform superposition over S.
Okay, sorry. Okay, this is just the definition of cat S. Okay, then now I see it. Thank you.
Yeah. Okay. Great. Okay, so we're going to speed up a little bit, and my question is this really secure?
Sorry, Omri?
Yes.
I mean, couldn't you just say that the state you get back from the US is also a tensor product state? So if you measure, I mean, the way you've written it, it's not immediately clear, right? But the state is a tensor product state, so if you measure the second register, the first one remains undisturbed.
Yeah, so what Nico is clarifying is that if you look at this notation, it's not super clear immediately why this actually stays S, but for every X, you can think about it as having clauses around the 1 and the X. For every X, I'm going to have the same qubit here. And if I'm having the same qubit here, I can write it again as a tensor product between, just like I did here, between S, but this time and 1, and not 0. And then it would be actually easier to see yes.
I have a question about the public key. So if I understand it right, it's an obfuscation of the verifying function in a way, or like membership function. So if I have free choice over the public key, can I just use the constant, this is always right function, obfuscated, and then it's indistinguishable from a normal public key? So if I send someone money and he wants to check it, the function always evaluates to valid?
Oh, but you're right that you can do this, but we have to think about incentives. So the point is that the entity that generates the public key, you can think about it as the bank. If I'm as the bank, I'm going to mess up the verification.
I see.
Yeah.
Okay, thanks.
Okay, we need to speed up a little bit, and if somebody saw that I'm lying a little bit and why this isn't really secure. Yes? Yes.
So I didn't really understand. Is S like generated for each quantum money?
Yeah, so, you can.
So in a sense, this public key is like used for only one unit of money. So it's not like a public key in the classical sense.
You're right. So in terms of connecting these public keys to public keys infrastructure, for example, that we know in classical cryptography, you do need a classical public key, a different public key.
And you sign the public key.
And you can think about your universal public key as the signature key of the bank.
Okay.
And then everyone can see the classical signature key of the bank, and every time the bank wants to generate a new quantum money state, it needs to generate a new S and a new obfuscation of the membership checkiness.
Okay, thank you.
Yeah, okay. So this is not secure. Why isn't this I just revealed it, but let's see why it's not secure. Given this superposition of S, I can just measure this superposition. If I measure a uniform superposition over any subset, I'm going to get a uniform sample, uniform classical sample from S. And this is clearly clonable. This is a classical state, and the adversary is going to output these two X's, and they're going to pass verification, because what's the verifier really only doing is checking something in superposition, fine, but checking membership in some set S. Okay, and the point is that forging can be easier than cloning, and this is one example. But I want us to, be able to upgrade this verification, because the problem wasn't really in the scheme or the state. We know that the state is unclonable. The problem was in the verification. So what was missing inside the quantum verification of V? What was really missing is that V didn't check for quantumness. So let's be a bit more specific here. V checked that you have a superposition which is constrained to some set, but it did not check that you have a non-trivial superposition. It did not check that you have, for example, more than one element in your superposition. So what we're going to, and this is an important paradigm in public key quantum cryptography, these two checks, you need to check for range, which the verifier actually did. It did check for range, but you also need to check for quantumness. So only elements from some set S, but also many elements from some set S, if it makes sense. But how do we achieve this? Let's remember what went wrong here. The verifier really just checked membership. But one thing that we get out of this verification, this faulty verification, is that after this verification, we do get something non-trivial, which is a superposition of elements that are constrained to S. So here is my question. Let's say that I have this set, and I have a superposition that is constrained only on S. Now I want to check for quantumness. What do I mean I check for quantumness? I want to check that I have a non-trivial superposition after I go to this state. And I can do this if S has the same conditions for before, but also it's a subset, a subspace. This is a very nice observation by Aronson and Cristiano. So what is a subspace state? This is just the same as before, just S is not generally a set, it is a subspace of the strings of length n. Again, a uniform superposition. And I'm going to define the dual subspace, which is just all the strings, all of the n-bit strings that are orthogonal to all of the strings in S. So I'm going to denote by S-perp all of the x's, such that for any element in S, the inner product, modulo 2, obviously, is going to be 0. And a very nice, known from before that work, property of Fourier transform and subspaces is that if I'm doing a quantum Fourier transform mod 2, or in simple words, just a Hadamard transform on a subspace state, I'm getting the subspace state of the dual subspace. This is just a calculation. Okay, so we have this lemma here, and now I want to use it to improve my verification. So here is the question. I have two distributions, D0 and D1. In D1, I'm getting a random classical element in S, and in D0, sorry, and in D1, I'm getting the full uniform superposition over S. And now I want to distinguish between D0 and D1. And there is a small hint here. What happens if I do a Hadamard transform? We know what happens to D1 if I'm doing a Hadamard transform, right? I'm just going to get this. What happens if I'm doing a Hadamard transform to a classical element? What I'm going to get is a uniform superposition. But the important part of this sentence is that if I'm having a superposition which is constrained to some subspace S, the wider the superposition, if I'm transforming it using a QFT, the narrower it's going to be after the transformation. So if I'm having something very narrow, for example, a classical state, it's going to blow up to a uniform superposition. And if I'm having something which is maximal, which is the entire uniform superposition over S, I'm going to get something which is smaller than all of the elements, which is all of the elements that are in the dual subspace. How does it help with verification? This is the previous verification. I'm going to just concatenate a second part of verification. So the second part, now I'm going to have two oracles for S and S-perp. And the first part of verification is going to stay the same, and the point is that I know that after the first part of verification, I have this constrained superposition. If I have a constrained superposition and I'm doing a Hadamard transform, now I'm expecting to be constrained to S-perp, and this is exactly what I'm going to check. I'm going to check the second check, going to be exactly the same as the first one, but instead of checking membership in S, I'm checking membership in the dual of S. And what was shown by Aronson and Cristiano in 2012 is that if you do this two-part verification, this is actually secure. So if you check that you have only elements in S, and then you do this QFT and the dual check, and you check that intuitively that you have many elements in S, you should be fine. But this is a statement with respect to an oracle. And this is the construction. Just output this for a random subspace. Use ideal obfuscation, and this is why it's not a construction in the standard model. I'm assuming ideal obfuscation, which we know that we, a lot of the time, don't know how to construct. Question?
I realized I'm kind of confused by one piece of notation. So when we write cat S, we mean a uniform superposition of all elements of S?
Yeah, exactly. It's yeah. Mm-hmm. Okay, so we succeeded in constructing a public key quantum money scheme with respect to a quantumly queryable classical oracle. Okay, we are not going to have too much time to see the proof in the standard model, but I do want to touch upon the main points of this transition from the oracle construction and the construction in the standard model. Yeah, so we know that we want to do it under computational assumptions, and what Zandri showed in 2018 is that if you keep the construction exactly as it is, the only change that you do is instead of assuming this idealized obfuscation, you use quantum secure indistinguishable I/O for classical circuits. The scheme is secure. So this is all the same, but you can use I/O in order to obfuscate the membership checks of S and S pair. And the main technical tool, which repeats itself throughout public key quantum cryptography a lot, is this lemma, which states a property of I/O, and it says that if we assume quantum secure I/O, and we also assume quantum secure injective one-way functions, then the following two distributions are going to be quantumly indistinguishable. So the first one is that I'm just going to take the membership check of S. I'm going to obfuscate this circuit as it is, and I'm going to give you this obfuscation. The second distribution, I'm going to do the following. I'm going to first sample T. And what is T? Condition on S. I'm going to take a random superspace of S of a bit larger dimension. So the dimension of S is n over 2. The dimension of T is 3n over 4. And it's going to be random conditioned on being, on containing S. And I'm going to give you an obfuscation of T. And this is going to be true for every S. So even if I fix S, and only then I do this random experiment, it's still going to be indistinguishable for every S. I don't even need to pick S at random. Because the secret really is the delta between S and T. Okay, let's just state the statements without seeing the final proof. And it was also shown that if I have two fixed subspaces, T0 and T1, and S is between them. So S is going to be the only entropy here. Shweta, you have a question?
Yeah. The previous slide?
Yes.
Yeah, so can you give some intuition why this theorem is going to hold? Because these two subspaces are not even the same size. I mean, I guess you can pad S, but I mean, it's not the same function. So you have to do hybrids, right? So what is the main idea? Like, why is it going to work?
The main idea is that you are going to, all that I need to prove to you is that if T is, it doesn't have too much of a large dimension, because obviously if T has too much of a large dimension, for example, T is all of the elements, all of the n-bit strings is going to be distinguishable, right? Because the circuit, if T is too big, this cannot be
then you can, yeah, sure.
Yeah.
You can sample and just check.
Yeah, I can just have the two, even oracles to S and all of the oracle that always says yes, and I'm done. So this is why you can actually have an inequality here and not the dimension is bounded by n3 and over 4. And the proof is, the heart of the proof is going from S to S perp with one extra dimension. And I can do these steps as long as the extra dimension,
as you didn't grow
as long as I didn't blow up too much.
Okay.
And okay.
Sounds good, thanks.
Okay, and another thing to say is that if I sample S with a constrained entropy, so I have these two fixed subspaces, T1 and T0, and S is between them, so T1, the smaller one, is n over 2 dimension, and the bigger one that contains S is 3n over 4. and S is going to have entropy conditioned on this condition, it is still going to be information theoretically hard to clone S. And you can show that this verification that we just seen by Aronson and Cristiano, it's projective, which means that if I successfully verified, I actually projected the state that I got, which is an arbitrary phi, into this rightful state, which is ket S. The combination of these things actually gives you the full proof of why, if you use subspace hiding, and the fact that the projection, the verification is projective, you can show that if you manage to trick the verification, because of the projectiveness of the verification, you actually manage to clone. And if you manage to clone, you can blow up the subspaces. This is actually what's, I have maybe 1 more minute, 2 more minutes. Ah, amazing, we have time. Okay, let's see the proof sketch. So the first hybrid is just the adversary trying to clone, trying to forge, and it succeeds with some noticeable probability. This is the first hybrid. Now we use subspace hiding for the first time, when we're going to blow up S to T0. So I'm going to, instead of obfuscating S, after I sampled S, I'm going to sample T0, a superspace of S, and I'm going to obfuscate T0 instead of S. And this is going to be indistinguishable from the first hybrid because of subspace hiding. I'm going to use subspace hiding again, but this time I'm going to blow up S perp into T1 perp. Again, by the same reasoning, I'm using subspace hiding, I'm going to be indistinguishable. Make sure that because these hybrids are indistinguishable, also the success of the adversary of cloning is going to stay indistinguishable. And now I have this S between T1 and T0 because S perp is a subspace of T1 perp, which means T1 is a subspace of S. So I just have now S between T1 and T0 with these corresponding dimensions. And now I'm just going to do this simple trick, the information theoretical trick, that instead of sampling S and then T1 and T0, I'm going to first sample T1 and T0 and then sampled S conditioned on this. Then I can fix by an averaging argument the subspaces, T1 and T0, and actually show that you exactly break this entropy, reduced entropy cloning that we saw. The thing that you break is this. Yes, Nico.
Quick question. It seems the first 2 hybrid switches that you did, replacing these obfuscated oracles for S and S perp with T0 perp and
T1.
With T0 and T1 perp. It seems like that didn't change, that didn't break functionality, right? So from the adversary's perspective, nothing changed. The question is, why didn't you already define the real scheme with T0 and T1 perp instead of having an S oracle?
So you're asking why not just
exactly define the real scheme?
Put like T0 and T1 on the board?
I mean, into the oracle, right?
Yeah, but what's the advantage of changing from?
Well, I mean, you could have essentially saved these steps in the security proof then.
Okay. So if I'm doing it, okay. So Nico's question, and with this we're going to conclude, is that, okay, you just show me a security proof, and this security proof moves to an hybrid where you don't really give obfuscations to S0 and S1, you give obfuscations to T0 and T1 perp. The reason that I don't do this in the original construction, that if I would have done this in the original construction, I would not be able to claim that the construction is projective. Okay, and then one of the steps in the security proof breaks. So I need to start small and then move using subspace hiding, and then only I can show that you actually break an information theoretical statement. Okay, so if anyone interested, I can talk about the proof more in the break, and we have public key quantum money under cryptographic assumptions, and yeah, that concludes the talk. Thank you.
Just, I think you have time until 11 according to the schedule, but yeah.
I have time until 11?
Right, so the first three lectures, each day are an hour and a half, and then the last one is just 1 hour.
Ah, and I was speeding up, okay.
But
I could start the second one, and it's longer.
I'm not sure if coffee is ready there, so...
Maybe you can do the last part.
Okay. So we have a lot of time.
Yes.
I was sure that
So,
it's written in the...
Can you in particular, I didn't follow how you concluded. So I came until hybrid 3, but I didn't see how, I didn't understand how you concluded the argument. So this is fine. This is
one.
fine.
This
All
one.
this is fine. After this.
After this.
Yeah, this I didn't get.
Okay, so because the dual check is projective, so what we were doing until now, we can actually use the time to start the second lecture, but let's see. Okay, so the point is this. I'm starting from hybrid 0, and every time at the end of each hybrid, what I'm going to check is the state passes verification. I know that if the state passed verification, I need S and S pair for it to pass verification, and I know from the projectiveness that if it passed verification, I actually have the state. So at the end of hybrid 0, I have the state, also hybrid 1, 2, 3, and so on. And now I have this, now I'm going to do this. At the end of hybrid 3, we actually have 2 copies of ket S. And we can fix by an averaging argument. Until now, what I did, I was sampling T1 and T0, and then condition on being contained between them, I sampled S. And then I did my hybrid 3. So now what I'm going to say that, well, I know that in hybrid 3, which looks like this, I know that the probability to clone is noticeable. So at this point, I'm going to forget that I know S, and I'm going to say that by an averaging argument, there exists T1 and T0, such that for this specific T1 fixed and T0, for a random S, the adversary successfully clones. This is this step. Okay, so this exactly breaks the information theoretical statement from before. Why? Because I forgot S, but I fixed T1 and T0, and I now have a random subspace of dimension n/2, conditioned on being contained between T1 and T0. And what the adversary really breaks, after the averaging argument, I have an adversary that after I fixed T1 and T0 and I gave him this state for a random S, it still managed to clone. And the statement that it breaks is exactly this one. Right? These are the exact conditions that I just violated. Okay, so it seems that we have more time than I thought. So what I think about doing, if that's okay, I'm going to present a problem, which is going to be the starting point of the second lecture. If that's fine. Okay.
just a few more questions.
Sure.
Yeah. So when you go back to this construction of this public key quantum money, how do we sample this subspace? It's just like all possible subspaces, and then we take one uniformly, or how does this work?
Right. That's a good question in classical computation. So how can I sample an n over 2 dimensional classical subspace? What I can do, this, nothing related to quantum here. I can sample the first vector, and it's going to be my first vector in S. Then I'm going to sample a second. This is going to be like a rejection process. A second one with probability 1 minus 2 to the minus n. I'm going to be outside the span of the first one. And this vector is also good. So every time I'm going to add one dimension, and as long as I'm not adding too many dimensions, with high probability for each of my samples, it's going to be outside the subspace that I already have in the ith step. So this is a sampling in steps. And in the ith step, I'm trying to increase my dimension of S by 1. And I'm doing n over 2 steps.
Okay, thank you.
Yeah.
And another small question is this theorem by Aronson and Cristiano. I think it said like something like theorem 25, like they have this many theorems. It's like a really long paper, a big paper, or it's...
okay.
I was just curious. I don't know if I've ever seen like theorem 25.
I don't know if it's
maybe it's a different counting or something. But it's,
what was the question?
No, it's just the number of the theorem, if they have this many theorems in their paper.
So I'm not sure if there are 25 theorems or 25 claims, and some of them are theorems. I think that the second one is the case, but it's a kind of a heavy paper. Yeah.
And the final question is just a more practical one. So I don't know if you can answer this, but do we already have technology or devices that can store quantum states indefinitely?
Not even close.
Okay, so this is what we are just assuming for now. Okay.
Yeah. Not even close. And these states are also, we're not even close, and it's even worse than that because we're not only trying to preserve a quantum state. Notice that what we're doing here is obfuscating classical circuits, and then the verification, what the verification does is doing a classical computation in superposition. So the quantum circuits that are actually going to implement it inside this verifier are going to be at least as big as the classical obfuscations. And we know that classical obfuscations are basically, they're polynomial, but they are huge. Polynomial.
Okay, thank you.
Okay. So we saw how to construct private key quantum money. We saw how to construct public key quantum money. And for the next, let's say, 10-15 minutes, we are going to see something. Okay. Yeah, sorry for the confusion in the time. So what we are going to see in this second part. In the second part, we're going to present, again, start with a problem. It's going to give us some motivation for why we think that we solved a lot of things, but not really. We're going to see another central tool in public key quantum cryptography, which is called tokenized signatures. We're going to see some techniques for tokenized signatures. And we're going to spend most of the talk on an object called semi-quantum money, which presumably solves this problem. Okay, so what is the problem that I want to talk about in this part? We know that we already have public key quantum money, and that's great. And now Alice wants to send to Bob her quantum state, and she can send it to Bob. But now Bob decides to be malicious, even though it can verify the state just fine, and it's going to say that it didn't get anything. And Alice doesn't know what to do, because how can you prove, now I have this unclonable state, and I sent it to Chris, and Chris just says that he never got it. And this is unclonable, so I don't have another copy to show, I don't know. So this is a problem. Okay, that's one scenario of being malicious. Let's think of another one. Alice can decide to be malicious, and it's going to tell Bob, prepare, I'm sending my state, and then just don't send it. and nobody can prove actually anything. And there is another scenario where both of them are perfectly honest, and Alice is going to send the state, but now the channel is faulty. And I don't even know why the channel is faulty. It can be faulty because it's just bad technology, or it can be faulty because I have a man in the middle. I don't really know. The state is now susceptible to basically everything. Everything and anything. And this state was unclonable, and now Bob got something that's garbage, and the point is that this is not any quantum state. This is an unclonable quantum state. It costs money, or it can be any other thing, a copy-protected program, or anything that public key quantum cryptography has to offer, and it got destroyed. So this is the problem that we are going to talk about in the second part. So this is like a promo. And so the question that we are going to try and answer is, now I have unclonable quantum states, and I want to actually do two things. I want to guarantee that I sent it, and I want to be also able to not guarantee, but also prove to the world that I actually sent this quantum state to the other side. Yeah, let's stop here. I think that's enough. Thank you.
Do we have any questions to Omri? Yes.
Yeah, just another small question. I just realized, so in this private key quantum money we could like create as many quantum states as we wanted, right? With the with this. So in this public key, maybe I missed it. We just can create it a single time, and then we cannot. Okay, we also create copies as the bank.
So in order to create the state, I just need to know S. So I didn't say this, but there is a classical algorithm for sampling a random subspace of dimension n over 2, but there is also a quantum algorithm that, given this classical description of S, I can efficiently generate cat S. So as long as you have the basis for S, you can generate cat S. So this is your mechanism for generating public key quantum state. If this was your question.
I guess in this application for the next talk, I guess there is not the bank. It's not involved. It's just two parties that just got like a coin or like a quantum state, and they want to.
Yeah, I mean,
because they cannot, like Alice cannot just have like multiple copies. It's just assumed that.
Right, multiple copies. So the whole point is quantum money is that the quantum state is what worth money. Yeah. And if I have more than one copy, I have times the money times the copies.
Makes sense. Thank you.
Okay.
I think Michał has a question.
So in the construction we used indistinguishability obfuscation for the membership check, and given that actually the secret is only the set S, is it possible to exchange indistinguishability obfuscation for some lighter primitive? Well, it's clear that FHE doesn't solve the issue, because then you would have to decrypt it and this breaks the security. But is there anything else that we can use in place of I/O?
Yeah, you just stated one of the important problems in the field. So how can you? So the heavy part is using indistinguishability obfuscation, quantum secure indistinguishability obfuscation. We don't know, if I understood your question correctly, of doing anything lighter in terms of computational assumptions or just efficiency of the construction that still gives us public key quantum money. It's a big open problem, for example, to construct it from lattices. There was an attempt about a year and a half ago about Peter Shor. It turned out to also be broken. It's a process. Yeah.
I think Michał has a question. You have a question, right?
So, if I understood well, there is a possibility to classically verify the issued money, or
Classically verify
after the quantum state is expired, or is it that when the secret key expires, we can no longer verify it all?
Okay, so if we're thinking about either, I'm not sure that I got the question, but let me try. If you're thinking about either secret key or public key quantum money, you have to have the key to verify. But was that your question? Or?
Because the question is, what do we do if we have the state that expires in 3 seconds, say? Can we build a quantum chain of secret keys that can verify each, or is it impossible?
What exactly expires?
The key, because the quantum...
So you mean you set a system that it is agreed in the system that in time t, the key is no longer valid?
Yeah.
I think that depends on the system. You can do that, but then... So you're asking what to do if you have a system like this, and you want to, and your, for example, okay, nice. So what you're asking, if I understand correctly, is that you have a system like this, and I can verify the public quantum state until time t, but now it's expired, but I'm an honest party, and I have this state when I can send it to someone that still has the key to be refunded or something. That's the motivation?
Yes.
Yeah, you can, as long as again, any entity that has the public key, or the secret key, and 2, has the power to refund you, you can, yeah, but that depends on the agreement in the system.
Okay, thanks. Any more questions? Yes, we have a question over there.
Yeah, we don't have ideal quantum circuits, so each quantum circuit introduces some error. And what about error accumulation? So I suppose that when we execute this quantum circuit for membership check, then sometimes this error will accumulate and our quantum money vanishes, or not.
Okay, so that's a good question, because we always want to add more properties to our schemes. One thing that people actually work on is trying to construct public key quantum cryptography, in particular public key quantum money, that has many properties of error resilience or error correction. The only thing that's nice in the scheme that we saw is that it is projective, which means that I have this state, and over time that we know for quantum mechanics that things get slowly decohered. And because it is projective, it moves from the noise a little bit from being the correct state, but every time that I verified it, I make it again the correct state. So I can reproject it to be the correct state every time. But what you're asking is something even deeper, because you're asking about the actual verification. So what happens if I error in the thing that's supposed to correct my errors? And that's a big problem, generally in quantum computation. But people are trying to think about schemes that, yeah.
We have one more question.
Yeah, now that we have all the time you want, I wanted to ask whether you know what the status is of this old proposal to base public quantum money on knot theory by Farhi Gossett. Sure.
Yeah, so what Chris is asking about is one old and known candidate for not even, it's a lot stronger actually than public key quantum money. I think it's equivalent to a thing called quantum lightning, which we didn't define. And so I think it's just unknown. So if you assume this, and this event really boils down to a classical computational assumption, so the security you can, the best that we know is that there is some scheme to construct public key quantum money based on problems from topology, from low dimensional topology, from knot theory. And yeah, we don't know anything formal to say. There is a very nice trick there in the verification, which is very different from the verification here. But it boils down to a computational assumption on the quantum states, not even, yeah. So we don't know.
Okay, we have time for even more questions. Nico, maybe you would like to ask a question?
I think we have a...
You have a question to ask?
No,
okay. Okay, good. Then let's thank Omri.
I think we have one more question.
We have one more question. Okay, good.
Very short.
Yes, okay.
Can we bound an amount of issued money?
Can we bound?
So, like, can we somehow certify that we issue no more than 100 coins?
I didn't get it.
That we issue sign no more than 100 messages or no more than 200 messages.
I'm not sure that
I think the question was basically about preventing inflation. So could you prove that you didn't issue more than a certain number of coins? I think that's what.
Okay, yeah. That's about the behavior of the bank.
Behavior of the issuer, yes.
Because the things that I showed today, no. But the thing that we actually will see here, under some very heavy system, yeah. Very inefficient, yeah. You could control the bank.
Yeah, because that's where, like Bitcoin is supposed to shine.
Yeah, exactly. That you don't do whatever you want as the bank and do inflation and stuff like this. Yeah.